So let's start today's session. In previous sessions, we have learned about Australian experience with energy transition by Professor Ken Bowen. We also learned from Professor Andrew Blakers about renewable energy generation, and Professor Paul Burke about carbon pricing, one of the policies to enable the transition from fossil fuel to renewable energy. Today, we are going to learn about international renewable energy system. We will hear from Dr. Bin Lu about the idea of super grid for Southeast Asia from technical aspect. We also hear from Professor Ken Bowen and Dr. Tom Longden about aspects of trade in hydrogen, the emerging promising type of fuel. Dr. Bin Lu, the convener of today's session, is a fellow here at the Australian National University. He has done a lot of research in modeling of electricity system, especially interconnections among the countries, focusing on Southeast Asia. And he has won several academic awards in electricity system. Professor Ken Bowen, you met him in previous sessions, is internationally renowned expert in energy transition. He has a lot to share with us about energy transition. And today, especially the topic is about the trade of hydrogen. And also joining Professor Ken is Tom Longden. He's a fellow here at the ANU. Tom is an economist focusing on energy and other related issues. And he has recently published in very high-ranking journals, including Nature Energy. And I myself, you met me in previous sessions also. I'm a convener of this course. Also, I've done research on renewable energy in Southeast Asia. So today I will be sharing with you the topic of a cross-border electricity trade within Southeast Asia. And our facilitator today, as usual, is Tarek, and you've met him already. So I may not need to introduce more. Now I would like to hand over to Dr. Bin Lu, today's session convener, for the introduction of the agenda and also his first part. So over to you, Dr. Bin.
Thanks, Tom and Nico. I will share my screen now. Can you see my slide?
Yep.
Perfect, thanks. So, good morning or good afternoon, everyone. It's my pleasure to welcome you all here today to session 4 of our Energy Transition Partnership Roundtable Executive Training. So this session is International Renewable Energy System. Today we will have 3 presentations. The first presentation is Electricity Supergrid by myself. I will talk about the technology and the cost of building a supergrid across Southeast Asia. The second presentation is ASEAN Cross-Border Electricity Trade by Dr. Tom Du. And our third presentation will be from Professor Ken Bowen and Dr. Thomas London regarding hydrogen trading. And we will have 2 Q&A sessions. So if you have any question during the presentation, please use the Q&A function on the Zoom, and we will answer your questions in the Q&A session. So today we will also have an opportunity for everyone to participate in the discussion. Is it better to export renewable energy as electrons or as molecules? So renewable energy can be exported as electrons through high voltage transmission lines or export as molecules through electro fuels such as hydrogen. So I look forward to hear what you think. So let's start with electricity supergrid. So I will start with the war of the current. In the late 1880s, there was an argument, a debate between Nikola Tesla and Thomas Edison regarding the use of alternating current or direct current technology in the power industry. So direct current, DC, runs continually in a single direction, while alternating current, AC, reverses direction a certain number of times per second, like 50 or 60 hertz. So this is known as the war of the current, AC versus DC. So who won it? Nikola Tesla, the left, right? So AC, alternating current. Today, our power industry operates at a frequency of 50 or 60 hertz. However, in the recent decade, the advances in power electronics technology, direct current DC becomes more and more important in our power industry. So high voltage direct current HVDC technology is well positioned for, firstly, long distance bulk power transmission, transferring gigawatts of electric power over thousands of kilometers. So I will give an example. And secondly, submarine and underground power cables. So if you design a submarine or underground power transmission longer than, let's say, 100 kilometers, the only option is HVDC, high voltage direct current. And thirdly, for electricity grid interconnection, so because of the DC to AC conversion, the interconnected electricity grid are actually decoupled. So this will avoid the failure of one system to be transmitted to another system, avoiding a wider coverage of power blackout. Example, so this is the Changji to Gukun HVDC link in China operating in 2018. It is the world's most powerful transmission line. It can transfer 12 gigawatts of electric power over a distance of 3,000 kilometers at 1,100 kilowatts. The transmission loss is relatively low, see about 3% per 1,000 kilometers. So it's about 10% in total for this transmission line. So here you can see the image, the towers and transmission lines, overhead transmission lines. Another example is the North Sea link. So this is the world's longest submarine power cable and will connect the electricity grid in Norway and the UK. So it is 1.4 gigawatts, 730 kilometers of submarine power cable, and 525 kilowatts. This is the operating voltage. So here's the image. You can see the converter station that power electronics. So, is it possible to build a supergrid across the Asia Pacific? Basically, this hypothetical supergrid is a high voltage direct current HVDC transmission backbone in Southeast Asia, which is denoted by the red line on this map. So, as you can see from north to south, the Mekong region, so Hanoi, Vientiane, Yangon, Bangkok, Phnom Penh, and Ho Chi Minh City connected together through HVDC transmission, and then it's extending to Kuala Lumpur, Singapore, and to Brunei, Banassevi Begawan, and to the Philippines, Manila, Cebu, and Davao. So this HVDC transmission backbone also extends to Indonesia, Medan, Jakarta, Banjarmasin, Makassar, Maluku, Papua, and also to Dili. So the solid line on this map are overhead transmission lines, where the dashed line are submarine power cables, so undersea power cables. So there are possible extensions to China, to Bangladesh, to India from Yangon and Hanoi, and also extensions to the south to Western Australia and the Northern Territory of Australia from Singapore, Jakarta, and Dili. So, the research question, number one, is an Asia-Pacific supergrid technically feasible and economically competitive. Number two, how the Southeast Asian power industry will benefit from a fully integrated electricity market. So let's start with the electricity consumptions in Southeast Asia. So this graph shows per capita electricity consumptions in Southeast Asia. So the unit is megawatt hours per person per year in 2018. So as you can see, the per capita electricity consumptions in most countries are relatively low, only about 1 or 2 or 3 megawatt hours per person per year, compared with 9 in Singapore, 10 in Australia, and 5 in China. So consequently, there would be a huge increase in the near future in the electricity demand, right? So the 2020 electricity demand in Southeast Asia is about 1,200 terawatt hours, which may increase to 7,500 terawatt hours if all the countries achieve 9 megawatt hours per person per year, similar to Singapore. The likely huge increase in electricity consumption will have a large impact on energy security and the environment. So at the end of 2020, the proved coal and gas reserves are 44 gigatons and 4.6 trillion cubic meters respectively. So if assuming a per capita electricity consumption of 9 megawatt hours, they can only support less than 20 years. The annual carbon emissions from electricity and heat production are 644 megatons. So if current electricity generation mix in Southeast Asia not changed, then the carbon emission would increase to 4,400 megatons every year. And the annual premature mortality related to coal-fired power would increase from current about 20,000 to more than 100,000 deaths every year. So if Southeast Asia continue to rely on fossil fuels. So Southeast Asia needs energy change, transitioning away from fossil fuels to renewables, solar and wind energy. This is a soil radiation map. So yellow and red colors represent excellent solar energy resources. So in general, solar energy are abundant nearly everywhere in Southeast Asia. So that small circle is the land or water area required to power Southeast Asia with solar energy, which is about 1% of the total land area in Southeast Asia. So solar panels can be installed on rooftops, deployed underground, floating on water, and integrated with agriculture. So in addition, we can see that solar energy resources are even better in Australia, in northern Australia. So this is the competitive advantage of Australian renewable energy, and this is also the motivation to connect Australia and Southeast Asia through a submarine power cable. So this is solar, and how about wind? So this is a wind resource map, the wind speed. The regions with high quality wind energy resources are highlighted in red. As you can see, significant wind energy resources are widely distributed in northern countries such as Laos, Vietnam, and Philippines. But they only exist in few regions in the southern countries such as Indonesia and Malaysia. Therefore, if we can build a super grid across the region, then the wind energy can be moved from the northern country to the southern country, right? However, renewable energy, solar and wind energy are variable and uncertain in nature, so we need energy storage to stabilize renewable power generation. So this is a map of pumped storage hydro resources in Southeast Asia. Note that I'm not talking about conventional on-river hydropower. It's not conventional hydropower built on the river. This is off-river, closed-loop pumped storage hydro. The combined storage potential, the result potential is about 2 million gigawatt hours in total. So pumped hydro is well positioned for large-scale energy storage. There are no material availability or supply issues compared with battery. It had low water consumption and moderate environmental footprint compared with on-river hydropower. It had a long service life, 50 to 100 years, compared with only 5 to 10 years for battery. I think in the future renewable energy system, pumped hydro storage and battery storage will be complementary. Okay, so how much energy storage is required to support 100% renewable electricity? Let's look at this graph. The horizontal axis is rated power in gigawatts, and the vertical axis is storage volume in gigawatt hours. We model scenarios with and without a supergrid to make comparison. So these are the storage requirements in the countries to support 100% renewable electricity without a supergrid. And the total here is the sum of energy storage requirements in all the Southeast Asian countries without supergrid. So we can see the total storage requirement are 2,400 gigawatts for power and 45,000 gigawatt hours for storage. In comparison, the supergrid scenario, the storage requirement reduced to 1,200 gigawatts for power and 16,000 gigawatt hours for storage. Consequently, the storage requirements are more than halved in the supergrid scenario. The reason is it's because of the sharing of renewable energy resources across the region. So remember the result potential, the energy result potential is about 2 million gigawatt hours. So this number is only about 1 or 2% of the potential site. And this would be enough to support 100% renewable energy system in Southeast Asia. Another graph, so this is the electricity generation. Again, we model the scenarios with and without the supergrid to make comparison. The total is the sum of electricity generation in all the countries without the supergrid. So compare with total and supergrid, the total electricity generation is more than 10,000 terawatt hour per annum, while the electricity generation in the supergrid scenario is only about 8,000 terawatt hours. So this is because renewable energy supply can be effectively smoothed out through the supergrid, so the energy spillage is minimal. And we can take a closer look. So on this graph, yellow is solar, green wind, blue hydropower and other renewables, and green legacy fossil fuels. So solar energy is the major source of electricity in many countries like Cambodia, Indonesia, Malaysia, Myanmar, the Philippines, and Timor-Leste. And wind energy integration is only significant in Laos, Thailand, and Vietnam, right? Two countries in Singapore and Brunei, natural gas compete with battery storage for energy balancing. So in total, solar energy 80%, wind energy about 15%, and the fraction of legacy fossil fuels is smaller than 5%. So in the supergrid scenarios, we can see that the green bar, which is wind energy integration, is greatly increased. So this is because the supergrid allows moving of wind energy from the northern countries to southern countries, and therefore it can promote wind energy integration. So lastly, how much it costs? We calculate the levelized cost of electricity, including electricity generation, storage, and transmission. So this is the all-in cost. As you can see, the cost figures in Laos, Thailand, and Vietnam are relatively low, where the cost figures in Cambodia, Indonesia, Myanmar, the Philippines, and Timor-Leste are relatively high. So overall, the average cost, the weighted average, is about $102 per megawatt hour, compared with $98 per megawatt hour in the supergrid scenario. So despite there is a large investment on the supergrid on the transmission infrastructure, the cost figures decreases in the supergrid scenario, right? So, in summary, the Asia-Pacific supergrid is technically feasible through HVDC technology, high voltage direct current transmission, and it is also cost competitive compared with the national electricity market operating independently. And we can see the benefits of building a fully integrated electricity market are multiple. So electricity generation facility can decrease by 20%. Wind energy integration increased by 70%, and energy storage requirement reduced by 65%. Thank you. Okay, so our second presentation is about cross-border electricity trade in ASEAN, and I would like to introduce Dr. Tang Du. Over to you, Tang. Tang, you're muted.
Thank you very much, and sorry. Now I would like to present the case of cross-border electricity trade within ASEAN, so Association of Southeast Asian Nations. We learned from Dr. Bin Lu's presentation that the super grid within the region, which facilitates the cross-border electricity trade, would bring about substantial benefits, including cost saving, more smoothing out effects, more renewable power uptake, and more electricity access for remote areas. Let's have a look at the theory of cross-border electricity trade. What are the models for trade of electricity? Cross-border electricity trade can be classified into bilateral, multilateral, or unified. In terms of bilateral, we have unidirectional bilateral trade, as a case of Thailand and Laos, or bidirectional bilateral trade, in the case of Laos and Vietnam. So the countries can import and export electricity. The next level of trade is multilateral. So it's getting more complicated. And it allows either unidirectional transition or the multi-directional among differentiated markets. Or as the next level is a market directional among harmonized markets. So moving from bilateral to multilateral, the degree of integration and complexity increases. As the highest level of trade is unified. For example, North Pole or Australian National Electricity Market have this form, in which all generated electricity would be cleared in an unified market. So this is the highest form of unification of cross-border electricity trade. This graph shows us the status of cross-border electricity trade in ASEAN. And as we can see here, electricity trade is very tiny, only about 4%, compared with other energy trade, for example, in dry natural gas or coal, or trade in total goods and services here. Electricity trade in ASEAN is very tiny, very limited. And that also indicates a huge potential of increasing cross-border electricity trade within Southeast Asia to reap the potential benefits that Dr. Bean and I just mentioned. I'd like to have a question for you. Have you ever heard of the concept of ASEAN Power Grid before today's session? Please put in the chat box yes or no, so we can have yes, yeah. Interesting. So roughly we have half and half yes and half no. I can see from the chat box. ASEAN started talking about ASEAN Power Grid since 1997. So quite a long time ago, about 25 years ago. However, the progress has been slow and limited. The majority of our trade has been bilateral between the neighboring countries and mainly in Mekong countries, especially between Laos and Thailand. Although ASEAN is gearing toward increasing the electricity trade and aiming at multilateral, I think it can be fair to say that the countries are far from full multilateral, multidirectional trading. And this table shows us the existing interconnections. ASEAN aims for 16 projects, interconnection projects within the region. And so far, only 7 projects with a total capacity of around 8,000 megawatt have been established. Many other projects have not started yet, and the existing capacity is far from the target that ASEAN has set. So why has the cross-border electricity trade among ASEAN countries been so limited compared with the potential? There are multiple barriers. First, the countries tend to prefer self-sufficiency. The countries want to keep the amount of imported electricity to minimum, and thus associated with sovereignty and nationalism. For example, Indonesia has regulations allowing for possibility of electricity import, but also prioritize national generation capacity. Also, there's limited willingness to rely on foreign electricity sources, and partly because of national security concerns. For example, Singapore chose to rely on imported LNG to power about 95% of its electricity generation. So generally, there's a lack of trust in importing electricity in terms of cross-border electricity trade. There are also other technical and institutional barriers. As we know, ASEAN countries are diverse in the region, geographical dispersion, and they have high diversity in standards and specification. So make it hard to harmonize the technical specifications. Also, as you know, the electricity data are considered as sensitive, and people are not very willing to share information publicly. Also, there's resistance from incumbent utilities because many countries in ASEAN now have monopoly power, state-owned electricity provider and generators. So of course, they don't want to change the status quo, and they have quite strong lobbying power for not changing. For example, in Singapore, the market of electricity market structure in Singapore is competitive wholesale market. And Singapore was quite reluctant until recently to join the project of Laos, Thailand, Malaysia interconnection. So that's the incompatibility of electricity market structures among the countries. Also, there are some economic barriers. For example, to have the multilateral trade or to establish the unified market, we will need to have a coordinating agency. So there are some costs involved in either upgrading existing institutions or establishing a new single centralized entity to facilitate the multilateral cross-border electricity trade. Also, there's a risk of disputes. Currently, there's no institutional mechanism for dispute resolution for cross-border electricity trade internationally and regionally. That makes countries reluctant to invest. And also, private sectors is not very keen on investing in such a huge cost and high risk infrastructure, such as cross-border electricity supergrids. Also, cost sharing, who will pay more and who will pay less. It's very hard to discuss and to agree. One important point here is environmental and social costs of traded hydropower. In the Mekong region, the majority of traded hydropower comes from dams, hydro dams, and those hydro dams have very high external costs to the local community downstream, and also environmental services. And of course, the countries that suffer from the hydro dam developments may not be willing to buy and support electricity trade. So there are many barriers. How to move forward, how to overcome the barriers to increase the cross-border electricity trade. First of all, political and social support are very important. If the countries can be more comfortable in relying on the trade electricity, on importing electricity, if the society support more of the trade of electricity, then it will be easier to overcome other technical and economical barriers. Also, as the case of Laos and Thailand shows very clearly, if the countries focus on bilateral trade for the time being, for the decade or so, then they will be able to build the necessary infrastructure and also have time to harmonize other technical aspects. So if ASEAN wants to increase electricity trade, we recommend that they focus on bilateral trade first and later move on to multilateral trade mode. Also increase sharing information about hydro dam operation will build more trust. And also, as Dr. Bin pointed out, ASEAN has a lot of potential of solar and wind and off-river pump hydro storage, which can replace new development of hydropower. And we believe that if the countries move towards solar and wind, then environmental and social costs of cross-border trade will be less, and that would encourage more cross-border electricity trade. And technically, the HVDC interconnection will also help the process. So those are the solutions that we are proposing. And of course, there might be other solutions that you can also have and be able to share. We are having a journal article in press called ASEAN Ready to Move to Multilateral Cross-Border Electricity Trade. And please check it out. It will be ready in a month or so. I also put the question for you, a mini survey for you in the Moodle site, and I will also put it here. So it's a very quick survey. If you can click on this one and also on the course website and share with us your opinion. When will the ASEAN Power Grid be finished, in your opinion? By 2030 or later? So I will pause here. Thank you.
Great. Thank you very much, Dr. Tang, and Dr. Bin also for the presentation. So I think now we go for a question and a bit of a discussion. So if you've got any questions, please either put them into the chat box or you can ask them directly. I'll call to see if anybody would like to ask a question directly now. It can be to either of the two speakers. So we've heard about high voltage regional grids, and we've heard about different kinds of trade between the countries, regional trade. Does anyone want to put their hand up for a question? Maybe while people are either typing or waiting, asking their questions, I've got a couple, one question for you, Dr. Bin. You showed that in the cost analysis, that the cost of electricity from a high voltage DC regional grid is more expensive in Cambodia and Indonesia and less expensive in other countries. Can you explain a little bit why the costs would vary between the countries? Is it to do with the size of their electricity market or their role in the generation of electricity? What's the reason there that they differ between the countries?
Yeah, thanks for your question. So the cost figures included in the graph, including electricity generation, storage, and transmission. So there's the trade-off between energy storage and electricity transmission. So if you have more energy storage, you will need less transmission requirements, and vice versa. So in the super grid scenario, I assume that all the countries connected together, and then the electricity trades can be occurring between the countries, and then calculate the total cost of generation assets, storage assets, and transmission infrastructure. And it shows that the number for the super grid scenario is about $198 per megawatt hour. It's higher than some countries and lower than some countries. It reflects the, Southeast Asian countries have different electricity consumptions, also the different renewable energy resources. It reflects the difference between the countries in renewable energy and electricity demand.
Mm-hmm. Thanks, Dr. Bin. And there's another technical question for you, Dr. Bin, from Lan in Vietnam, which is, which model or software did you use to simulate the scenarios in your research?
Yeah, the software is called FIRM, F-I-R-M. So it's developed at ANU by myself. Basically, it's an energy balance model. So energy generation and demand are balanced every hour throughout 10 years. So electricity generation, storage, and transmission are co-optimized. It's not just optimized generation or storage, it's co-optimized in the model. So after simulation of the scenarios, you got the best configuration or the optimal mix of electricity generation, storage, and transmission. Apart from firm software, I also use different softwares for renewable energy resource assessment. For solar and wind energy resource assessment, The software is SAM, S-A-M, developed by US National Renewable Energy Lab. And for pumped hydro resource assessment, the software is called STORES, S-T-O-R-E-S. It is also developed at ANU by myself. So all the software are open source, which means on GitHub, which means you can download it, use it, and modify it.
Great, thanks, Dr. Bin. So there's a question now from Serpa from ETP. If the supergrid does not proceed in a timely manner, what is the alternative? Is it collaboration in fossil fuels? And what is your conclusion of the trade-off between the supergrid and other ASEAN programs for regional, say, gas pipelines and clean coal collaboration projects?
Okay, so I will answer first, and I think the future is renewable energy. So we will see energy transition from fossil fuels to renewable. The reason is simple. On the slide, you can see if all the countries achieve 9 megawatt-hours per person per year of electricity consumption, then the fossil fuel resources cannot work in Southeast Asia. It can only support less than 20 years. So in this way, we need to transition to renewable energy because renewable energy is abundant, especially solar energy in this region. So I think apart from the development of the supergrid HVDC transmission backbone, I think in every country, renewable energy transition would be important work in the near future. So renewable energy is the future and fossil fuel will be the past. Tang, any thoughts from you?
Yes, I agree with you, Bin. I think that the first option would be ramping up renewable energy in each country. That's very important. And secondly, increasing cross-border electricity trade, but focusing on bilateral trade instead of multilateral or deep integration. That would be more practical for bilateral. And the countries, especially in the Mekong regions, have existing interconnections and also have existing and in pipeline projects to increase the bilateral trade. So that's my response. Thank you.
Maybe just one aspect of that question to touch on again with you both is that the conclusion, what's the trade-off there between the supergrid and, say, regional gas pipelines? Dr. Tang, you showed in your presentation that there's much more trade on energy than there is in electricity. So is it, do you see that these things could replace some of that investment in the gas pipelines? Is that the intention?
I think that ASEAN is thinking of developing both the supergrid and the gas trade rather than replacing each other. So I think that the ASEAN, let's say ASEAN and the participants here may have more to share with us that pursuing both. But in my opinion, the trade in gas seem to have stalled recently for various reasons. And the countries are considering LNG instead of the fixed gas pipeline. So yeah, perhaps other participants, I noticed that some said that they have joined in ASEAN development of the supergrid and also the energy development plan. May be able to share more. Thanks.
Yeah, if anybody else, there was one comment that one colleague has been involved in the ASEAN Interconnection Master Plan number 3. So if anybody wants to make to contribute there, please put your hand up so we can unmute you and involve you in the discussion as well. In the meantime, we have one more question from Magfira Ramadani. So the question is related to the differing costs in the countries. And the question is, to what extent does different levels of market liberalization impact on the progress or the feasibility of the supergrid? So each ASEAN country has different levels of market liberalization. So what's the impact of that on the supergrid?
Let me start answering first, and Bin, you may have more to add. Yes, the difference in the level of market liberalization does affect the idea of cross-border electricity trade. And it makes it very hard for multilateral or uniform types of trade. That's why we propose that the bilateral trade might be more suitable, because the two countries, it will be easier to negotiate and perhaps to agree on the power purchase agreements than multi-countries if they have different market structures. Mm-hmm. Yeah, that's my answer.
Yeah, so I would take the Australian national electricity market as an example. So the Australian electricity market, the national markets, there are 5 states: New South Wales, Queensland, South Australia, Tasmania, and Victoria. Actually, these 5 electricity markets are also weakly interconnected. So currently, the Australian energy market operator developing integrated system plan. So this plan is to look forward for the next 2 decades, like 20 years, to see how we can build renewable energy resources in distributed renewable energy zones. How can we develop transmission lines? So which transmission line should be taking priority over others? So I think the first step for ASEAN countries to build a supergrid or a fully integrated market is to work together and make a plan.
Great. And there's a question from Pauline. She's asking about the resilience of the supergrid. So how resilient would the supergrids be against natural phenomena, for example, earthquakes, and how could pricing be established across borders in terms of standardizing the cost, the pricing?
Yeah, the supergrid can be designed according to the N-1 or N-2 principle. So N-1 means if you lose a major transmission line, the whole system can work as normal. N-2 means if you lose 2 major transmission lines, the system can work as normal. So that means we will have redundancy in our transmission design.
Okay, and a question about how do you see power wheeling mechanism in the supergrid? This, Dr. Bin, for you, I guess.
Yeah, so if I understand this question correctly, you are asking about the electricity trade between the countries. Is that right?
Are you there? Yes.
Yeah. So I have to say, renewable energy resources are quite different from conventional fossil fuel system. So, or conventional hydropower system. So, for example, currently in Laos is a net energy exporter, which export hydropower to neighboring countries. But in the 100% renewable energy system, the power flows will be multi-directional. So it will flow from one country to another country during morning and then reverse direction at night because of the diverse renewable energy, solar and wind energy resources in the region. So in that way, the transmission line will be more complex than the current single direction export transmission line, such as for Laos export industry.
Okay. With all of these questions that are emerging around this like kind of power wheeling and trade and standardizing pricing and so on, how would a super grid like this operate? Because you've got national electricity markets which are operated under kind of national jurisdiction. How would it interact with those kind of national operators, and is there a need for a regional operator for something like this for both of you?
Yeah, I think I can start first. The cross-border electricity trade is about wholesale market. Okay, so there will be trade within the wholesale markets of the countries. The retail markets will be still remain under the jurisdictions of each country. There will be the need to establish a regional coordination entity, so to oversee and also to regulate the regional market. And as I mentioned, it's very hard. And over the last 2 decades or so, the ASEAN, and especially the smaller number of Mekong countries, could not have agreed on, for example, where to locate such an entity. So that's difficult part. And if the countries want to move further along the ladder of integration, then things are getting more complicated. So yeah, that's about the coordination of the regional.
Yeah, I think electricity is also a commodity. So the Regional Comprehensive Economic Partnership, RCEP, was signed in 2020. I think electricity can also be traded under this framework. And regarding the operation of the electricity market, and I would expect there will be central dispatch and regional dispatch. So just like a different sub electricity market, there will be balancing market to achieve a real-time balance between renewable energy generation and electricity demand.
I've got one final question on scale. So Dr. Tang, you showed in your presentation that there's different types of trade, you know, from bilateral up to unified. Are there sort of like scales that best suit, like when you make a decision to go from, say, like a bilateral towards a more unified system and towards more what the supergrid would be? And you know, what's the optimal scale that we're looking at? Is it the ASEAN region, or should we be considering things like Dr. Bin mentioned of connecting to India or to China or to larger, you know, to go even bigger than this if we want to look at regionalization?
In theory, the more integrated, the better the trade policy system will function. However, in practice, there are many costs involved in terms of scaling up. So it depends very much on the region and on the issue at hand of the project that will determine the optimum level. So, for example, for ASEAN, we are thinking of bilateral and perhaps multilateral, but very simple model involving a couple of countries would be optimal, taking into account costs and benefits.
Mm-hmm. Dr. Bin, any?
Tang and I were also working on modeling of a supergrid in the Great Mekong subregion. The Mekong subregion, including 5 countries and 2 provinces of China, and it demonstrated that this supergrid is very useful because it reduced the requirement for energy storage and reduced the cost significantly because it can share the wind energy resources and hydropower within the Great Mekong subregion. So that's a smaller scale of the supergrid in Southeast Asia, but it's connected to a regional electricity market of China.
Okay, so the regional grid could take on different types, bilateral, multilateral, unified, and it could also take on different geographies if we're considering it. Okay, I think we've probably maybe I pass back to you, Dr. Bin, to move on to the next section. And we can, if there's any questions we haven't asked, then I'll look through the chat and we'll ask them in the next session as well.
Okay. Okay, so it's about 2 o'clock in Canberra. So I think perhaps we can move on to the next presentation. So our third presentation will be from Professor Kim Bodwell and Dr. Thomas London regarding hydrogen trading. Over to you, Kim and Tom.
So good afternoon, everyone, and I'll now share my screen. So here we go, in this session where we're going to talk about hydrogen trading. Of course, this is a new development in the energy scheme of things, and it has, if you like, some parallels with trading systems that have happened previously, but we believe that there are differences in how this might develop. Let me now share a screen. Can you see that okay?
Yep, can see it.
All right. I'd like to now hand over to my colleague, Dr. Tom Longden, to talk about the first part of the presentation.
Yep, if you just hit the next slide, I'll start. Hello, everyone. I'm Tom Longden, so a research fellow here at ANU. We'll be talking about hydrogen and some of the interesting developments that are happening around the globe in terms of who's positioning themselves as either an importer or an exporter of hydrogen. Ken, could you just hit to the next slide?
Yep, here we go.
I've still got the first slide showing.
Okay, this could be, let me stop sharing. It's kind of gone into a presenter view or something. So let me go back. All right, now let me try it again. How does that look?
Perfect. Thanks for that. So yeah, as I mentioned, we'll be talking about the developing and the potential trade for hydrogen. There's been a lot of interest in hydrogen, and you can see here what we've done is separated the key countries in terms of how they've positioned themselves. You can see there that Australia and other countries, Norway, Chile, Saudi Arabia, Brunei, have positioned themselves as potential exporters with a large range of potential importers. So there's a lot of different countries that have developed hydrogen strategies. And it's interesting to read those hydrogen strategies because many of the countries have very different positioning in terms of what they hope to achieve with future hydrogen. And embedded in that is also the type of hydrogen production and basically other low carbon energy carriers. So it's really interesting to also note that even though hydrogen and the trade of hydrogen is still quite young, there are initial pilot demonstration projects that are occurring where we do have small amounts of hydrogen being traded. Most of those projects do not, or all the projects that we know of do not involve green hydrogen at the moment, which is produced with renewables. What's happening at the moment are there's small demonstration projects between Japan, Australia, Saudi Arabia, Brunei that are basically testing out the infrastructure needed to trade hydrogen via ship. And those projects use different carriers. And at the moment, there is uncertainty in terms of how trading will evolve, and that will be our focus today. We won't talk too much about the technological determinants of future trade, other than to discuss that there are different types of energy carriers liquefied cryogenic hydrogen, liquid organic hydrogen carriers, and also ammonia are feasible. But really, we're at the stage where we're still seeing, pilot and demonstration projects around the development of shipping and storing the technologies needed to export hydrogen. The production of hydrogen is well established, but it's really the export and the shipping of hydrogen that is uncertain and playing out as we speak. So we're going to talk about two examples in terms of oil and gas that are quite interesting because they'll set sort of a framework or examples for how hydrogen trade could develop. So next slide, thanks, Ken. So this is a map of the global liquefied natural gas trade in 2019. So this is an industry that was developed over the last few decades and has now got into quite large scale exports and imports across the globe. And there you can see that we've mapped out the different interregional trades and exports and imports. So Australia is quite a notable export of LNG. I think it rivals some other countries in terms of being the largest exporter of LNG. And a lot of Australia's LNG does go to Northeast Asia, especially Japan, on long-term contracts. Next slide, please. So in terms of this analogy, one of the reasons why it's quite interesting and dynamic is that in terms of hydrogen, the quality and the consistency in the molecule of hydrogen, once it's produced, doesn't change. So even though you might change the way you store hydrogen, at the final point, that hydrogen, when it gets used in a fuel cell, basically does not vary by quality or any other measure, other than the embedded carbon content based on how it was produced. And so that's where a lot of the discussion around hydrogen is being developed at the moment. Is a lot of discussion is about how you produce hydrogen and really focused on that carbon content. So whether you use coal, gas, or renewables, that carbon content changes a lot. Where for oil and gas, so the actual consistency, the quality of those fuels changes based on the sulfur and hydrogen content. And gas also has a Renewable index that basically tells you the differences in the consistency and energy embedded in that gas as well. So at the moment, oil is used, and oil and gas basically work through trading hubs. There are different types of contracts. Oil tends to be spot and future markets. Gas, especially LNG, is based on long-term supply contracts. And in the Australian case, those long-term supply contracts actually helped establish the industry in the long term and have those LNG exporting facilities, importing facilities in Japan established. Where hydrogen, there is now the uncertainty of how that will play out. So the questions there that Ken will address and discuss in the next half of this presentation, we'll talk about how hydrogen may develop and how hydrogen trade may develop. It's quite likely that that will be on long-term supply contracts because there is notable infrastructure needed, either in terms of storage, the shipping, and even that sort of refueling and infrastructure at ports. And also the question of trading hubs, because the fact that the consistency in the molecule of hydrogen is basically, once it's produced, is the same, then that means that you can have similar sort of situations to oil and gas where you do established trading hubs. But bear in mind that a lot of the debate about the complexities of hydrogen and how you produce hydrogen is quite important because the embedded carbon content changes a lot between whether it's produced with coal, gas, and renewables. Even with carbon capture and storage, there's still a quite heavy carbon content for hydrogen from gas. So over to you, Ken.
Great, thank you, Tom. So what we need to consider, as Tom's just mentioned, is how do you trace the amount of embedded carbon that is in the hydrogen production chain And one of the methods for doing this is called hydrogen certification, which in itself is a very hotly debated area. And we've produced a paper here that we published in the journal Energy, which talks about the way in which you might go about building up a hydrogen certification scheme that provides a validation for the amount of embedded carbon that is used in the production and the transportation and the delivery of hydrogen to the market. So we call this the policy challenge of defining boundaries for emissions accounting. And really this is all around the boundaries of the different steps in the process, starting with the extraction of the raw materials, the generation of hydrogen itself, the storage of that hydrogen, the transportation, the refining and delivery of that hydrogen to consumers. So at every stage, you have to keep track of the amount of embedded carbon, and that's where this boundary idea comes into play. Now, there are a number of other ways of doing this. They're called, for example, the guarantee of origin. That scheme really is saying that, you know, if it's hydrogen produced from renewable electricity through electrolysis, then it's given a label of renewable hydrogen, which has effectively no embedded emissions. Or if the origin is from steam methane reforming from natural gas, then that has, if you like, another origin in the fossil fuel process that releases greenhouse gases, et cetera, et cetera. And so by just simply labeling the production type, you are telling the end user how this was made, and that gives you some feel as to the amount of embedded carbon. And similarly, you know, the technology used to produce it is also relevant, particularly when it comes to the use of carbon capture and storage as part of the technological process for delivering the hydrogen. But really, the only effective way of certifying the carbon content is to track in a validated way the amount of emissions at every stage in the production chain to give you a number for the embedded carbon dioxide. And this is the method that we favour, and this is the reason we talk about the different boundaries. So it's important to use this modular approach where you look at the fugitive emissions from extracting, say, for example, the methane in steam methane reforming. Then you look at the emissions involved in, you know, transporting and delivering the feedstock to the plant. You look at the emissions produced by the plant, let's say CO2 from coal gasification. And then you've got to look at storage emissions. If there are, you know, compressors used that employ electricity that is generated from fossil fuels. And then, of course, transport emissions, where the transport itself may employ fossil fuels. So at every step of the way, you add up the emissions and you come to some final number associated with the amount of embedded CO2. So that means that you could envisage a future hydrogen trading hub which buys hydrogen from a number of different generators. Each of these generators has an embedded carbon dioxide emission intensity. We'll call that XI, which is the amount of CO2 emitted per kilogram of hydrogen produced. And then each of these generators creates a certain mass, MI, of hydrogen in kilograms. So you then simply effectively add up all the CO2 that is embedded in the hydrogen stored in the hub by multiplying these factors together. And at that point, you have, if you like, an average intensity for the entire hub, which is just really a summation of the intensities and weighted by the amount of mass of hydrogen that the hub has accepted. From that point, the consumers could act in a number of different ways. They might, for example, wish to purchase whatever emissions intensity the hydrogen average of the hub has. That's this value down here. Or alternatively, they may wish to purchase hydrogen which has zero carbon content. In other words, they only want renewable hydrogen with no embedded emissions anywhere down the production chain. So in that case, they're only interested in purchasing an emissions intensity of 0. Then there might be other buyers who might want to have a certain emissions intensity on average, where they would pay a contract for difference, if you like, for the carbon content from the hub, depending on what the average carbon content in the hub was at a particular time. And then there might be others who instead bypass the hub completely and simply buy from one of the generators using a long-term contract at the particular carbon intensity that the generator has for their production. So these are flexible ways in which you can imagine hydrogen trading operating either through the hub or around the hub, where the customers are then matching their needs from the various generators. How might this look? Here's a diagram that Irina has produced, which shows the imported demands in various parts of the world, the black dots, the various potential exporters, the white dots, and the possible trading arrangements that could occur. So there might be MOUs between countries and agreements that are in place for the supply of hydrogen of various carbon intensity. So what we see is potentially a number of models developing. As Tom mentioned earlier, the LNG markets were really kicked off by long-term contracts, which gave certainty at a guaranteed price in order that the investment in LNG could be de-risked. And you can imagine the same thing happening to kick off the trade in hydrogen. Over time, there might be various agreements to supply hydrogen from various parts of the world into a particular importer, which would blend the different types of hydrogen, whether they be renewable hydrogen or potentially hydrogen from LNG with carbon capture and storage, or even without carbon capture and storage. You could imagine a combination of those. And eventually a trading hub might develop, which would take hydrogen from various locations and blend it in the way that we described it previously, then on-sell it to particular users who require different embedded carbon intensities in the final product. So that's the opportunity that lies in front of us. Again, it'll be interesting to see how this develops, because this is a completely new market and it has a product which is effectively transparent for all intents and purposes as far as its carbon content is concerned, unless, of course, you have hydrogen emissions certification in place to tell you how much carbon was used in the production and delivery of that commodity. So that is the challenge that the hydrogen trading system faces, and it'll be interesting to see how the solutions for this eventually develop. So thank you for that, and we're very happy to answer questions.
Great, thank you very much, Tom and Ken. That was a really interesting presentation. So we have electrons and molecules. Can I invite anybody who has a question to raise their hand? If there's anyone who wants to ask a question directly, please raise your hand. In the meantime, we've got a few questions in here that have come into the chat, so I'll look through some of them. We've got questions that are relating both to the hydrogen and also, but they could also have potential for the grid as well. So one question on the hydrogen side is that for the archipelago part of ASEAN, so the question is, future archipelago power system could get better support from hydrogen and, say, ammonia trading than from a supergrid, because of higher degrees of freedom and the geography. From Ken or from Tom, do you agree that the island nature of ASEAN has a particular advantage for hydrogen trading?
I guess you've got to think about the infrastructure needed to support trading of any energy systems in an archipelago. Clearly, having lots of fixed transmission lines across the ocean is going to be incredibly expensive and maybe not very flexible. And that's really part of the reason why many island states rely on imported fuels of various description. And obviously, as fossil fuels disappear, the alternative is really hydrogen fuels. Then you have to think about what type of transportation mechanism you use, because for every island to have a liquid hydrogen storage and decompression, etc., facility, again, requires a significant amount of infrastructure investment. So again, technology will dictate the most appropriate type of facility infrastructure for the individual islands. And then you have to think about the end use. Is this going to be for fuel cells for vehicles? Is it fuel cells for providing energy for homes, for industry? And indeed, whether there is a fuel cell solution for the type of purpose that this is designed for. So these are all complex questions, but I take the point that it's really an infrastructure question, and that you want to avoid massive interconnectors going between islands in the case of electricity trading.
Yeah. For our regional trade and power grid team, Dr. Bin and Dr. Tang, do you want to say anything about this point about building supergrids or regional trade of electricity in the island context of ASEAN?
Yes, I think that's very interesting point. And it's hard to have a kind of binary answer, yes or no. But in my opinion, it would be still good for ASEAN to pursue the ASEAN super grid to some extent. The matter is the ambition, right? Practical steps, how to achieve it. That's my opinion. Thank you.
Okay. And a question for Tom. In your slide, one of your slides, you showed that there's some countries who are already identified as exporters of hydrogen, and other countries who are sort of putting their hands up as importers of hydrogen. What's the sort of the common characteristics of those exporter and importer countries that you see when you look across the list there?
Yeah, that's a really good question. I actually meant to mention that, because if you look at that list, you really see countries either who have notable gas assets or abundant land, sun, wind resources like Australia to produce hydrogen. And of course, those importer countries are typically those countries who are energy hungry, who don't have a lot of land space, and currently already suffer from energy security problems and are looking towards an additional use. The other country in there, so it's sort of coming to what Ken talked about with final demand use as well, is you'll see that some of those countries have also got a history of relying on gas for heating. And that has become a debate currently about whether hydrogen can be used for heating, especially with the crisis that's happening in Europe. But I think what's happening there is also that competing question of, can you electrify almost everything and what demand uses will you use hydrogen for. It also comes to the island question as well, because if you have that overlapping thing, you've got that competing discussion of electric vehicles versus fuel cell vehicles. And for me, one of the really interesting questions about that is the storage question, because and also the power question. So a lot of the initial applications you're seeing in the transport industry here tend to be smaller vehicles, but also heavy duty vehicles. That's where it makes quite a lot more economic sense in terms of, battery technologies not being ready to really produce semi-trailers or trains and things like that. Where it does seem that, say, electric vehicles for personal use and passenger vehicles have really got the first mover advantage. They're already on the market, and then you've got that question of refueling stations for transport. A lot of the possible uses, and what's interesting there is, say, the Korean hydrogen strategy is very much developed based on their links to Hyundai and producing fuel cell vehicles and other things like that, where the question behind those hydrogen strategies for those importer countries, you'll see a very different range of potential uses. Germany being interested in replacing gas, Japan really looking at even using it for power in potential applications, because they are quite energy hungry in that mean. But I think Ben was actually muted and wasn't able to respond before, so I'll stop here and let Ben have his say as well.
Actually, before Ben leaps in, let me just complete the answer to Tarek's question about the specific countries that are involved here. One of the points to note is that many of the importing countries are countries which lie in the northern latitudes, and these have, by and large, a winter demand peak. And this is the heating issue that Tom was talking about. And so what they require is seasonal storage, and seasonal storage is not going to be delivered by batteries. It's not even going to be delivered by pumped hydro. The only thing that can really deliver seasonal storage is hydrogen. So that's why there's such intense interest from northern latitude countries in hydrogen trading. And I think that, if we contrast this with the countries in the ASEAN region, for example, which have pretty much a uniform demand throughout the year, then that demand is much less in the Asia Pacific region. In the lower latitudes near the equator, the demand for hydrogen within the ASEAN region in particular is, I think, as was indicated in that question, more likely to be in the archipelagos, where you need some sort of fuel that you can use to store energy, given that you're not going to import it from your neighbours through transmission lines.
Right. Dr. Bin.
Yeah, I agree with Ken. So I think for the last topic, which I was muted. So for the island, I think solar energy and storage would be a practical solution in the long term, because the prices of solar energy and storage continue to fall rapidly. And so solar energy and storage will be fully cost competitive for lighting, electric cooking, electric vehicles, and other electric appliances. And so note that Southeast Asia is located in the Sun Belt. Sun Belt means, so in this region, the solar radiation is high compared with Europe and Northeast Asia. And seasonal variation of solar results is relatively low, and there is no significant heating load in winter. So, which means regarding energy storage, I think the region should focusing on large-scale energy storage, such as pumped hydro storage, and distributed energy storage, such as battery storage. Hydrogen storage will be useful in, let's say, for seasonal storage, as Ken mentioned, and hydrogen will also be useful in industry and transport sector. Apart from battery storage, pumped hydro, and hydrogen storage, we should also remember there's thermal storage, which is also useful. For example, the solar hot water, we can have solar hot water tank, hot water storage.
Right. So we see that there's actually a complicated planning exercise, isn't it? A complex planning exercise here. There is a case for some things, to be benefited by having a regional grid. There's a case for hydrogen being competitive in some types of loads and some types of contexts. And there's also a case, as you mentioned, Ben, just then, for let's say solar and battery to be on islands as a kind of an optimal solution. So something for the countries to think about is what are those advantages from these different systems? We have one question that's related to that on the energy storage side again. So one question is about hydrogen and batteries. So you've touched a little bit about some of the advantages of hydrogen as a storage compared to, say, batteries, but batteries and pump storage, but can you talk about a bit more about the two technologies, hydrogen and batteries, and when's it good to have one versus the other?
Yes, well, as has already been mentioned, in the transport sector, there is an advantage for large long-haul transportation in using fuel cells, because it's not possible to power a big truck or a train for long distance using batteries unless you do battery swapping, which is very infrastructure intensive. So the charging times for batteries are just too long to enable that to operate efficiently. So that's why you see coming onto the market the production of hydrogen fuel cell trucks and also hydrogen fuel cells used for trains in some cases. So there the delineation is really the scale of the transportation. So large scale hydrogen, small scale batteries, and also the distance, because you get greater range from hydrogen than you do from a battery currently.
Yeah.
So that's the transport sector. If we look at other sectors, if you're on a small island, which maybe has, I don't know, a fish processing plant because of fishing industry or something like that, and there's not enough solar to store in the batteries to enable a plant to run, you might have to think about hydrogen as an adjunct, in that case, to run a large fuel cell. Or there might be a particular type of industry on an island that requires hydrogen as an input to maybe, I don't know, used for generating high temperature heat, which is needed for a particular industrial process. But as Ben points out, by and large, most of the needs can be met with batteries. So you have solar installations on rooftops and in underutilized spaces that then provides you with electricity during the daytime and via battery storage also at night. But there might be islands which don't have enough area to do that, or they have heavy energy users, and maybe that's the opportunity then for hydrogen to play some role. But by and large, if it's a significant landmass, you will always find somewhere to put solar panels. For large islands or for continental use, that's inevitably the case. And so I think particularly in the low latitudes, hydrogen will have a less important role, a significantly less important role compared to batteries than you'll find in the higher latitude countries.
Great. We actually have on the call one person who was involved in the ASEAN Interconnection Master Plan that's been developed at the moment. So Aloysius, if you're there, maybe Nicole, could we unmute Aloysius? He'd like to say a few things about that master plan and how are these kinds of issues around hydrogen, regional grids being considered in that work? Aloysius, are you there?
Could you please raise your hand so I can unmute you?
Hello.
Hi, Aloysius.
Right.
Okay, I think we can hear you now. Great.
Thank you, Gederson. Thank you, Mr. Gederson. Hello, everyone. I'm Aloysius, or you can call me Damar. It's easier. I was in ASEAN Center for Energy working for the ASEAN Interconnection Master Plan study. I think there were also some ASEAN Center for Energy College here. There will be some updates on that one directly from the official institutions, the ASEAN Center for Energy, for informing that. But maybe last time during my involvement, we tried to update. I think Mr. Tang has presented very well. The issues we had so far are among the sovereignty, also the energy security issues, and also the contractual basis and the different market between each country around the ASEAN itself. However, the ASEAN is willing to do the interconnection because it will bring the benefits for the countries involved within the interconnection itself. And I heard also some updates that there will be more. Last time we are doing the modeling itself using commercial tools, and also we are doing with the grid interconnection approach. We involve some experts in the region and also in the world, like NREL United States, and also IEA, and also IRENA involved within the study to provide their inputs, which better scenario can accelerate the renewable energy penetration in ASEAN itself. And we found there are 4 scenarios. One is BU, second is the improvement of the ASEAN RE target, the third and the fourth are more and less we are seeing the more high penetration of the RE, and what are the impacts between the interconnection and between the contribution of each country in sharing their renewable energy penetration. Let's say somehow countries has their own renewable energy resources, like Indonesia, they have Kalimantan, they have a lot of resource, and Sumatra, they have a lot of resource, but the demand is in Java Island. So it cannot be tapped without the interconnection. And then after that, there are some also opportunities to tap the interconnection with Sarawak to the northern of the Kalimantan Island itself. And then after that, for Sumatra, there is an opportunity studied in the master plan to be interconnected with Singapore and also Kuala Lumpur, Malaysia. So there are findings that we can tap more renewable energy penetration that is locally resourced, but it will be also sufficiently provide the good demand to the demanding cities or the demanding areas in the countries itself. And of course, largely, it's not slow actually, but we have I think last time I do understand there are a lot of challenge around, but I think there are some improvement. Like last time there is an LTMS interconnection from Laos to Singapore, and I've heard also there is a initiative from Australia to also export their solar to Singapore, right? But I think last modeling it's not involving the Australia export to Singapore, but I think it's possible to also look around the potential around the Indonesia or in Philippines or in Malaysia and Laos. They have also abundant hydropower resources, pump storage as presented today, and also solar irradiation and wind, because in the future we also see a consideration of the low wind speed turbines to be commercially viable, I think, and in the next 20 or 15 years later with the certain development from now. So I think that's all I can share.
Yeah, right.
But happy to share more.
Thanks a lot, Damar. That's really useful. I just the ASEAN Interconnection Master Plan, the objective of promoting or developing and exploring this is really to look at improving the renewable energy penetration. So that's great. Is it, if we think of the types of regional trade that Dr. Tang had showed us, are most of the initiatives that you're exploring under the master plan under the bilateral, the multilateral, or the unified? Like, what is the master plan considering? Are you looking at bilateral trade, multiple bilateral trade arrangements, or you're looking at the more kind of stronger level of connection there? Sorry to put you on the spot, Damar, but if you have a chance to answer that one, would be quite useful, I think. Oh, could somebody please unmute Aloysius, please? Maybe I can.
Okay, thank you. Sorry, I was muted. Yeah, I think in the modeling we do not mention either it will be unilateral or bilateral or multilateral. But in another study last time in 2019, we collaborated with Papua, and also we collaborated with the IEA to identify the multilateral power trade in ASEAN. I think everyone can access it in the IEA website. There is several steps to improve the trading itself between the countries, from the unilateral to bilateral, and also from the bilateral to the semi-multilateral, and then after that the multilateral power trade.
Okay.
But it will take a long time to consider and implement the multilateral. But we are at this moment, from the studies in 2019 and 2020, we are only looking like unilateral or bidirectional. But maybe later it will be improved depending on the willingness of each country to see the multilateral power market in the region itself, and it will be also very important to be supported by each country in ASEAN itself.
Mm-hmm. Right. Okay. Okay, Tang, I see you shared a screen.
Yes. So I just would like to report briefly about the mini survey result. We received 31 responses, and here is the result. So the majority think that the ASEAN Power Grid will be finished after 2040, and you can see here, right? And this is the table. So 13 believe that it will be finished between 2040 and 2050, and 9 after 2050. Right? That's the majority of responses. Thank you. Just want to share with you. So you know the ideas of what people are thinking among ourselves.
Right. If I offer anyone an opportunity, if they want to, who voted for that 2030 to 2040 period, if you want to have a chance to explain why, please raise your hand and we'll get to you. Okay, so there's a couple more questions in here. One question from our colleague Setiawan Ari is about certifications for the hydrogen certification side. Setiawan, if it's okay, I might ask you to ask that question directly yourself, because I think it's quite a technical question and I may not get it right. So if you're there, Setiawan, I'll pass to you to ask that question.
Thank you, Tarek. Hi, Professor Baldwin. This is Ari Setiawan. So my question was that your approach on the modular calculation of parameter X1, it takes into account not just the production of hydrogen, but also transport, logistics, and liquefaction, and all that. So my question is that, is it fair if someone like buyer 4 in your slide wants to buy hydrogen with X equal 0, means 100% green hydrogen, while the production itself is green, but the transport entails quite a lot of emission in terms of electricity if it's not another green electricity or liquefaction or re-expansion of liquid hydrogen or ammonia in that case. So the question is it fair for a buyer to request X equals 0? Because this is in comparison with renewable electricity. Yes, it is possible to purchase 100% renewable electricity because the transmission accounts for very, very low, maybe less than 1% of the cost, so to say. Thank you.
Yes, it's a very good question. And indeed, it's not impossible, but you just have to be very careful. So let's go right back to the beginning. Before you even make the hydrogen from renewable electricity through electrolysis, for example, you have to get the water from somewhere. Okay, so maybe you pump the water from a river using a solar-powered pump, so you're not using fossil fuel electricity. Or you might have to use desalinated water from the ocean, which you desalinate again using renewable electricity to supply the desalination plant. And so your feedstock, which is water mainly, can be produced entirely with renewable energy. Then, of course, the generation process, as you mentioned, is itself carbon-free. But then after that, you've somehow got to transport the hydrogen. And there are different ways of doing that, requiring different types of energy use and all the rest of it. If you're going to liquefy it, you have to liquefy it using compressors, which have to be powered by renewable electricity. So maybe on the same site as you generate the hydrogen with your renewable electricity, you also got a portion of your renewable electricity devoted to the compression process. If you're using liquid organic hydrogen carriers, again, there's an energy cost you have to absorb from the renewable energy you're producing in the plant. And then, of course, you might then put this into a ship. Now, the ship, of course, at the moment would be running on fossil fuels, but you could imagine in the future that there are ships which are powered by ammonia, which you might be making using the hydrogen from your hydrogen production process. You might then convert that into ammonia using renewable electricity again, and using that to power the ships that then transport the hydrogen to the customer. And at the customer end of things, you then have to decant the hydrogen from the ship, store it again. And at that point, you can imagine if it was in an economy with fossil fuel electricity plus a bit of renewable electricity, you would then have to purchase green electricity from the market in order to carry out the processes at the end when you deliver it to the customer gate. So it's a process of being careful at every stage using this modular approach, but it's not impossible. And you can imagine how that could work.
Right. Okay, there's also a question here. Let me read it out. Based on the latest report from Bloomberg New Energy Finance, the Ukraine war has pushed up the natural gas prices to the point where green hydrogen is now cheaper than highly polluting grey hydrogen in Europe, the Middle East, Africa, and China. What are your thoughts on this? Could it be a pivotal moment in shifting international demand for green hydrogen instead? Or instead of considering other colors such as blue or grey hydrogen to boost the global energy transition?
I might start with that one. I just wanted to point out that it's an interesting time to be discussing that, but one of the big costs involved in producing hydrogen is actually the feedstock cost, whether that be gas or renewable electricity. I think off the top of my head, electrolysis with capital costs as they are now, in terms of dollars, production costs in terms of dollars per kilogram, 60 to 70% of that cost ends up being driven by the electricity cost that feeds into actually producing that hydrogen. That, of course, depends on some assumptions around efficiency and scale. I can't remember the numbers for gas on the top of my head, but one of the things to bear in mind when you do look at cost assumptions for producing hydrogen with gas is they tend to be quite large scale, but still the cost of natural gas into the process is a big determinant of the production cost. And actually, we've just submitted a paper with some colleagues in Germany And it's really interesting because they were running the analysis on our behalf. And in our last meeting, just before submitting the paper, they decided to put in a higher cost of gas scenario into the paper because it's quite a notable topic and it's a really big lever. And it's one of the things that's actually hiding behind a lot of the estimates that you might see out there, that achieving a $2 per kilogram hydrogen target, you need to really be mindful of what they've assumed as the feedstock cost. Because if you've got a high electricity cost, you've got expensive hydrogen from electrolysis and renewables, but then the same for gas. If you've got SMR with CCS and low costs for the gas and different assumptions for CCS, then you start getting very low cost estimates for natural gas-based hydrogen. And so definitely it's something that people are being really mindful of. And it was good to see those Bloomberg numbers show that as well.
And just on the geopolitical part of the question, I think the entire Ukraine conflict has really refocused people's attention on the need, not just for diversity of supply, but also the need to decarbonize, because Europe in general and Germany in particular are now incredibly dependent upon imported gas. And this only serves to illustrate that they need to plan even more urgently to remove that constraint and to move faster down the path of renewables. And this is, arguably one of the reasons that Germany is a little bit reluctant to be out on the front foot in this geopolitical situation, because they are really under the thumb of Russia in terms of its supply of gas to Germany. And this is a direct result of Germany deciding to remove its nuclear fleet in such a hurry. So they've made a number of decisions over a long period of time, which puts them in a very difficult situation. And they now have to completely rethink their strategy and move forward their shift to renewables even more rapidly.
Okay, thanks, Ken and Tom. I think I don't see any more questions. Are there any hands raised? Anybody would like to ask one last chance to ask a question? Otherwise, we'll pass back to Dr. Tang to take the next part of the class.